Very good evening to dear aspirants. I welcome you all on behalf of ESE Engineering Academy and ESE online platform. Now next we are going to take the part 2 of this session where we are going to discuss the important concepts for GATE and ESE examination. So I, Mohammad Waidullah, faculty at ESE Engineering Academy, will be discussing these things with you. Okay. So first is that we know very well that for building up a mechanism, we require some linkages, okay? And with those linkages, we should be able to check whether the relative motion is transmitted continuously or not. So if the relative motion is transmitted continuously, then that mechanism can be brought into application. And to check whether the relative motion is transmitted continuously or not, we have a very important law called as Grashof's law. So here, Grashof's law states that the summation of the shortest link, that is L minimum, plus summation of longest link should be less than equal to summation of links of other lengths. So here, L minimum stands for the shortest link and L maximum stands for the longest link, where P and Q are the values of those links which is lying between L minimum and L maximum. Okay. So if this law is satisfied, if this condition is satisfied, then we can say the relative motion is transmitted continuously. Okay. And there is one more statement to be added here. In order to transmit the relative motion continuously, there should be minimum one link that should undergo complete circular motion. Okay? Then only we are able to transmit the relative motion. And that one link will undergo complete circular motion when this condition is satisfied. Okay? So we know very well the inversions of 4-bar linkage. We have crank-rocker mechanism, double crank mechanism and rocker-rocker mechanism. So let us see the first inversion, wherein you can see the white color link is the L minimum. It is the smallest among all. And we are able to see the red color link, which is input, and the yellow color link, which is output. Both are completing circular motion. So here we can say that the relative motion is transmitted continuously. And this condition, that is L maximum plus L minimum, even this condition is also satisfied. So this is called as crank-crank or double crank mechanism. Okay. Similarly, another inversion, that is crank-rocker mechanism. So here basically in the first inversion, we were fixing the link number, that is L minimum we were fixing. This is actually L minimum we have fixed, and when we fix this L minimum, we are getting the result as double crank mechanism. Now in the second inversion, if you see here, if you examine thoroughly, this red color link is actually L minimum. Okay. So here we are fixing the link adjacent to L minimum. So in this inversion, we are fixing the link adjacent to L minimum. Okay. This is crank rocker mechanism. And we have fixed the link adjacent to L minimum. Fixed link is link adjacent to L minimum. So whether we are fixing the white color link or yellow color link, both the cases, white and blue color link, both are adjacent to red color link, that is L minimum. So when we fix these two, we are definitely going to get a crank rocker mechanism. Okay. Next one is rocker mechanism. This is a rocker mechanism, but if you see, the blue color link is actually L minimum, and we can also notice that this blue color link is completing circular motion. Okay, so in all these mechanisms, we should be having at least a minimum one link that is completing circular motion in order to transmit relative motion. So here this arrangement or this mechanism is called as rocker mechanism. And what is that we are fixing here? The fixed link is link opposite to L minimum. Okay, so here the location of L minimum is going to decide the type of inversion. So previously we have fixed the L minimum itself, we got crank rocker, double crank mechanism. Secondly, we have fixed the link which is adjacent to L minimum, we got it as crank rocker mechanism. And thirdly, we are fixing the link opposite to L minimum. This is L minimum. So when we are fixing the link opposite to L minimum, we get it as rocker mechanism. So fixed link is link opposite to L minimum. Okay, and we know that input link and output link both are undergoing oscillatory motion, but this L minimum will undergo circular motion. Okay, so if L minimum is fixed, then it will make the input and output as circular motion. Okay, so now let us try to solve a problem based on the Grashof's law, and based on that, how many number of links will be completing circular motion. We will try to identify even that one also. Okay, so let us see a question here. So figure shows a plane mechanism in which the figure indicates the dimensions of a standard unit length, and the slider C is driver and link AG, will it revolve or oscillate? This link AG, is it going to revolve or oscillate? We are required to find out. Okay, so now this complete arrangement, if we notice, we are going to disintegrate this into individual 4-bar mechanisms. Okay, we are going to disintegrate this into individual 4-bar mechanisms. So first linkage is that C, B and A. Okay, C, B and A is almost similar to a crank slider mechanism. Okay, so one linkage is linkage C, B and A. Okay, this is one linkage. The second linkage will be A, B, D and E. Linkage A, B, D and E. This is the second linkage. Okay, and in the same arrangement, the third linkage would be A, E, F and G. A, E, F and G. All right. So now, first let us try to understand whether this linkage A, B and C is a crank slider mechanism or not, or it is whether this is a Grashof linkage or a non-Grashof linkage. Let us try to understand that. Okay. So first is that I am disintegrating this A, B and C from the mechanism. So what do we get here? This will be point A and this will be point B and this will be the slider. Okay. Now here the length of AB is 6 and length of BC is 10. Now here the sliding pair can be converted into a revolute pair. So I need to replace this sliding pair with a link of infinite length when I am doing that conversion. Okay, so here I should be replacing this with r equal to infinite. About infinite, what is the radius of the straight line? The radius of the straight line is infinite. So here the point C will undergo rotation about a center which is located at infinite distance. So here this will be the center of rotation at infinite distance, and if I join here from the point A to this infinite center, I am able to form a 4-bar mechanism. Okay, so now from here it is evident that AB is L minimum. This AB is L minimum, that is equal to 6, and this is infinite, this is 10, and definitely by the measurement itself we can say that this could be L maximum. This could be L maximum. So L minimum and L maximum is already a infinite of a larger value. Okay, and this could be taken as P, and this could be taken as other link Q. Okay, so now if we apply the law, we get it as 6 plus infinite is less than, that is L max is infinite, and here this is also infinite plus 10 it is. All right, so here this is going to satisfy the Grashof's law, and now you are fixing the link adjacent to L minimum. This is the fixed link. This is the fixed link. Okay, and this link is adjacent to 6 units link, that is link adjacent to L minimum. We are getting here as crank rocker mechanism. So when I say here, if we are giving the translatory input to slider C, the AB is going to revolve. Okay, AB is going to revolve. AB, I should say, revolves. Okay, AB is going to revolve. All right. Now, similarly, if we consider another linkage, that is here Grashof's law is getting satisfied, and we are able to locate the link which is completing circular motion. Even that is also done. Okay. So next linkage, if we see, that is linkage ABD and E. So if you notice the linkage ABD and E, this AE is 4 meters and AB is 6 units and BD is 8 and DE is also 8. So definitely this is going to be L minimum. This will be definitely L minimum, and either BD could be L maximum or ED also can be taken as L maximum. Okay. So here L minimum is equal to 4 and L maximum is equal to 8 and P is equal to also 8 and Q is equal to, we are getting this as 6. All right. So now if you apply the Grashof's law onto this linkage, you'll find here 8 plus 4 is less than 8 plus 6. That is, this is a class 1 linkage, and in the class 1 linkage, what is that you are doing? You are fixing the L minimum. So when you are fixing the L minimum, we know very well that is link AB is going to revolve once again. Link AB is going to revolve. AB revolves, which we have already proven by considering the crank slider mechanism, that is C, B and A. Even same thing we are able to obtain when we are using this as a mechanism. So AB still, it continues to revolve. So here we can draw a conclusion, that is, if I am giving the input to C in the form of translatory motion, the link AB is going to revolve. This will be the output motion of the crank slider mechanism. And if AB is going to revolve, this AB becomes the input link for mechanism A, B, D and E, and DE is going to revolve. Okay, so AB becomes the input link for the linkage A, B, D and E, and we are also proving it. AB revolves as well as DE also revolves, because the Grashof's law is getting satisfied. Okay, even DE is also revolving. All right. Now, next linkage what we have is A, E, F and G. So, in that linkage also we are required to apply the Grashof's law and check whether are we getting the same answer or not. Okay. So, let me do it on this side. Once again, AE, which is equal to 4 meter, 4 units, and next is AG is equal to 6, and GF is equal to also 6, and GF is equal to 8. GF is equal to 8 units and EF is equal to 6. So now here this is definitely L minimum and this is L maximum. So L minimum plus L maximum, that is 4 plus 8, which is equal to 12. If it should be less than or equal to 6 plus 6. Okay, so it should be less than or equal to should be the condition. If it is greater than, if L minimum plus L maximum, if it is greater than P plus Q, then it is a case of non-Grashof's linkage. If it is a case of non-Grashof's linkage, none of the links in the entire linkage will undergo circular motion. None of the links will be undergoing revolving motion. Okay, so when none of the link is undergoing circular motion, which means continuous relative motion will not be transmitted in that given mechanism. Okay, you can call it as even also a non-Grashof linkage. Okay, so here is the condition, and an example for non-Grashof linkage is actually Ackermann steering mechanism, and this Ackermann steering mechanism is a part of ESE syllabus, wherein you can see, let me just recall Ackermann steering mechanism. This is for ESE guys. So in the Ackermann steering mechanism, you will be having a link, one link like this and another link. Both these two links, that is, this will be the linkage used in the Ackermann steering mechanism. So here the links AB and CD will be equal. They are not parallel, but they are equal in lengths. Whereas AD is greater than BC or CB. So in the Ackermann steering mechanism, you can find Grashof's linkage being used. Okay, for your understanding, you can go through the animation, but time being, this is a very important point for you to remember. Okay, so now here we can notice that A, E, F and G is also Grashof linkage. Okay, or I should say here we are getting equal to, so it is a case of special Grashof's linkage. And we know very well, once again, the AE is fixed, which is L minimum. That means the link AG and link EF are going to revolve. Okay, so here we can write a conclusion that the link AG and EF will be revolving. So here we are able to identify how many number of links that are going to complete circular motion. With C as an input, AB is going, under AB will be completing circular motion. AB is completing circular motion, then EF, ED will be completing circular motion. ED will be completing circular motion. Similarly, EF also is going to complete circular motion, and AG will also complete the circular motion. Now, I have missed one more linkage, I guess. Many of you are having a question that I did not consider. E, D and F. Linkage E, D and F. Here we are able to see three links connected by three revolute joints. Actually, this E, D and F will form a structure. It's not a mechanism. So generally you will find this three link arrangement or three member arrangement, especially in the trusses. So here this E, D and F is going to form a structure. It cannot be a linkage. Even if I consider, then I need at least 4 links. I need at least 4 links, then only I will be able to apply Grashof's law. So unfortunately, this is going to be a single link. This is going to be a one complete link. Okay? As EF revolves, ED also revolves. Okay? So please do remember here, guys. You can apply mobility equation also, and you can check for this one. So this is one of the problems of Grashof law, wherein we are able to apply it over a complex arrangement and identify within that complex arrangement how many number of links that are completing circular motion, and are we able to transmit continuous relative motion or not. Okay? So this is one of the problem. Now let us go to another one. Yes, another one, guys. We are going to discuss about the quick return mechanisms. So here is one numerical based on the quick return mechanism. So the length of fixed link in a quick return mechanism is 250 and the length of the crank is 100 mm. So here we are required to find out the inclination of slotted lever with the vertical in the extreme positions, and next is quick return ratio. Third one, we have supposed to calculate the stroke length, and fourth one is ratio of maximum velocities. So here what is happening here, that is the type of quick return mechanism is not at all mentioned to us. We are supposed to identify which type of quick return mechanism is given. Secondly, after knowing the inversions of crank slider mechanism, then only we can identify whether this mechanism is a crank slotted lever or a Whitworth mechanism. So let us go through the animations. This is a animation describing the working of crank and slotted lever mechanism. So in the crank and slotted lever mechanism, the slotted lever is going to complete oscillatory motion. Okay, the slotted lever is going to complete the oscillatory motion. Okay, next one we have is Whitworth quick return mechanism. This is the animation describing Whitworth quick return mechanism. Now in these two animations, these two are the examples of quick return mechanism. Even offset crank slider mechanism is also an example of quick return mechanism, but the students are more prone to confusion while they are studying about the crank slotted lever mechanism and Whitworth mechanism. Now guys, here if you carefully examine, this is the distance, or this is going to describe the length of fixed link. Okay, this is going to describe length of fixed link. Now, if I run the animation once again, you can see that this is going to describe L minimum. This is going to describe L minimum. Okay, this will be L minimum, length of the smallest link. Now, if you recall the inversions of Grashof under Grashof's law, that if we are fixing the link adjacent to L minimum, if we are fixing the link adjacent to L minimum, then what we get? We get it as crank rocker mechanism. We know that this wheel, this toothed wheel is going to act as a crank, and the slotted bar is going to oscillate. The slotted bar is going to oscillate. So this is an application of crank rocker mechanism. This is purely working on the basis of crank rocker mechanism. The oscillatory motion of the slotted bar is transmitted through this rod to the cutting tool over here. So slotted bar is going to oscillate, and definitely the cutting tool is also going to oscillate. So now if we recall the data over here, the length of the crank is 100 mm it says, and length of the fixed link is 250 mm, which means that this is definitely a crank slotted lever mechanism. Now let us try to identify the same thing. Is that can it be a Whitworth mechanism or not? Now, if you notice here, this yellow color link is representing L minimum. The yellow color link which is fixed, this is L fixed, and this is also L minimum. This is also L minimum. And when you are fixing L minimum, you can see the input link will complete circular motion, and the output link, which is slotted bar, even this is also going to complete circular motion. The difference between crank slotted lever mechanism and the Whitworth mechanism is that the slotted bar in the Whitworth undergoes circular motion, whereas in the crank slotted lever mechanism, the slotted bar completes oscillatory motion. That is the first important point. And here you are fixing the L minimum in the Whitworth mechanism, and here link adjacent to L minimum is fixed. Link adjacent to L minimum is fixed. Do remember that. Okay. So by any chance we cannot say this it is a Whitworth mechanism, because here it clearly indicates L minimum, which is equal to 100 mm, and this is definitely a crank. This is definitely a crank, and the fixed link, that could be L maximum or it could be anything. Let us not say this as L maximum, it could be P or Q, okay, which is equal to 250 mm. All right. So here length of the fixed link, guys, we also write this as distance between the fixed centers. This is the center of rotation of the crank, and this is the center of rotation of the slotted bar. So instead of writing this as CAP, we will represent this with C. C is called as distance between the fixed centers. And L minimum, I will be replacing this with the crank actually, because it is undergoing circular motion. So R we used to represent for, R we are using to represent the crank. All right. So now, next here, this could have been Whitworth mechanism if we are reversing the keywords. That is, if we are saying the length of the fixed link is 100 mm and length of the crank is 250, then this mechanism becomes Whitworth mechanism. I hope that confusion between the crank slotted lever mechanism and Whitworth mechanism is clarified to most of you. Okay. So now, first thing is asking you about the inclination of slotted bar with the vertical in the extreme position. So definitely this is a crank slotted lever mechanism, no doubt in that. Okay. So sometimes the clear indications will not be given to us, then we are supposed to recall the basics, and on that basis we are supposed to identify the mechanism. So R will be equal to 100 mm and C will be equal to 250 mm. So here the first bit says us to calculate the inclination of slotted bar with the vertical. So let me redraw the mechanism. This is the length of the fixed link. Okay. And at the extreme position, the crank is going to make an angle of 90 degree with the slotted bar. At the extreme positions, the angle between the crank and slotted bar will be 90 degrees. Okay. So this is the length of the crank is 100 mm and the length of the fixed link is 250 mm, and we are required to calculate the angle of slotted bar with the vertical. So let us write this angle as some alpha by 2. Okay. Let us write this as alpha by 2. So here we can write this alpha by 2, opposite to alpha by 2 we have 100 and 250 here. So I can write here, that is, if we consider the triangle O2, O1, and let us say this is A1. So if we consider the triangle in triangle O2, O1, A1, sine of alpha by 2 is equal to, that is opposite side O1, A1 divided by hypotenuse is O1, O2, that is R by C, it is R by C. So alpha by 2 is equal to sine inverse of R is 100 divided by 250. So upon solving this, we are going to get this as approximately alpha by 2 will be equal to, this is approximately 30 or 23.6 we are going to get. 23.6 we are going to get. And alpha will be equal to, this will be 23.6, and next this is the extreme position of the slotted bar with the vertical. Okay. Next is that we are supposed to calculate quick return ratio. So quick return ratio will be, this angle will be responsible for the cutting stroke, that is theta cutting, and this angle will be responsible for return. So let me just write this angle as beta by 2. So beta by 2 will be equal to 90 minus of 23.6. So 90 minus 23.6, that is beta by 2 will be equal to 66.4, it is 66.4. So quick return ratio, guys, that is QRR is equal to, theta cutting by theta return. So theta cutting is what? That is, the complete angle is beta and this above angle will be 360 minus beta. So this will be 360 minus beta. Beta is how much? 2 times of 66.4 divided by 66.4 it is. So 2 times of 66.4 is almost 133 or 134. 134 minus 360 will be equal to 134 minus 360. Yes. So this will be almost equal to beta by 2. Beta by 2, yes, here also I think this should be 2 times of, just let me write it properly. Let me write the formula clearly and after that I'll solve. This is 360 minus beta by beta. So 360 minus beta is 2 times of 66.4 divided by 2 times of 66.4. So 360 minus 134 is approximately 216, and this is 133. So 216 divided by 133 is almost slightly less than 2, slightly less than 2. Approximately we may get the answer as 1.7 or 1.8. Okay, so this will be the value of quick return ratio. Okay, and next one what we have in the question is they are asking to get the stroke length. So stroke length is actually the distance moved by the cutting tool. Okay, so from here, from this position to this position is going to tell you about the stroke length. Okay, just a minute. Yeah, this is another extreme position. So at both of these positions, we will see that the crank is 90 degree with the slotted bar. Here you can notice that the angle between the crank and slotted bar is 90 degrees. Here also you can see 90 degrees, and here also you can see it is 90 degrees. The angle between the crank and slotted bar is 90 degrees. All right. So this distance is going to tell us about the stroke length. Okay. All right, let us compute that. So these two are the extreme positions, and this will be giving us the information about the stroke length. This is theta c, and this will be stroke length. All right. So let us write this as point B1 and this as B2. Okay. Now if we consider this is alpha by 2, and let us say that this is another point at the middle, let us write this point as B. All right. So stroke length will be 2 times of B1B. Stroke length is 2 times of B1B. 2 times of B1 into B. Okay. So what is B1B? If you consider the triangle O2, B1 and B, B1B is opposite side to that triangle. Okay. In triangle O2, B1B, that is sine of alpha by 2. Sine of alpha by 2 is equal to opposite side that is B1B divided by hypotenuse will be O2B1. Hypotenuse will be O2B1. So O2B1 basically represents the length of the slotted bar. And what we have written under sine alpha by 2? Sine alpha by 2 is length of the crank by length of the fixed link. Okay. So B1B is equal to this O2B1 is length of slotted bar into sine alpha by 2 can be written as length of crank by length of fixed link. Length of fixed link. Now, here the stroke length is equal to 2 times of B1B. So I need to multiply here this with 2. Okay. So all the things are given to you, that is stroke length is equal to 2 times of length of slotted bar is given as 450 mm, okay, and 450 into length of the crank is 100 mm divided by 250, okay. So this will be 555s and this is 59s, and 5 by 9 means we will be getting this as 5 ones. This will be 1.8, okay, 1.8. So 2 into 1.8 is 3.6 into 100, that is equal to 360 mm will be the length of stroke, okay, in case of crank slotted lever mechanism, okay. In the crank slotted lever mechanism, stroke length depends upon length of the slotted bar, length of the crank and length of the fixed link also. In all these three parameters, the stroke length is dependent, okay. So this was the third bit in the question, and fourth bit is the ratio of maximum velocities. Ratio of maximum velocities, that is maximum velocity of slotted bar it is. Maximum velocity of slotted bar here, okay. So now let me recall that the slotted bar will be attaining the maximum velocity not at the extreme position when it is at the, or when it is vertical. The slotted bar will be attaining maximum velocity when it is vertical. At the extreme position, the velocity of slotted bar will be 0, okay. You can see over here also. At the extreme position, the velocity of the slotted bar is 0, and at the mean position, that is when it is vertical, the slotted bar velocity is maximum, okay. So one is that when the slider is upward, and the second one is when the slider is downward, okay. Now here if you notice, the input link is the crank and slotted bar. Now here at this point, this is O1 and this is O2, and let us say we are having here 2 points. A2 is on the crank and A4 is on the slotted bar. So here I can write velocity of A2, that is crank, point on the crank, with respect to O1 is equal to velocity of point A4, which is on the slotted bar, with respect to O2, because slotted bar rotates about point O2. Even in this case also, we can write the same mathematical equation. A2 will be here, just a minute. So here we can write the same condition, that is velocity of A2 with respect to this is O1, is equal to velocity of A4, that is point on the slotted bar, with respect to O2. So this is the fixed, this is the center of rotation of the slotted bar O2, and even this is also center of rotation of slotted bar. Now here the distance between O1 and O2 we call it as C, and this we call it as R, that is length of the crank. Here also this will be distance C, and this distance we call it as R. Alright, we call it as R. Now here this is one condition when the link number 3, that is slider, when it is at the top dead center, when the link number 3, that is slider, when it is at the bottom dead center. So now here velocity of A2 with respect to O1. For this situation, if we are writing R into omega of crank, is equal to velocity of A4 with respect to O2. A4 is also at the A4 and A2 are coincident, but they are in parallel planes. Behind A2, A4 is present. Behind A2, A4 is present. So distance from O2 up till A4 is C plus R. It is C plus R into omega of slotted bar. Into omega of slotted bar. Let me just write this as 1, guys. Let me write this as 1. Similarly, in the case 2, this is case 2, guys. I need to rename this. And this is case 1. Okay. In the case 2, if we are trying to solve, velocity of A2 with respect to O1 is R times of omega crank. Next, that is equal to velocity of A4 with respect to O2. A4 is very near to O2. Okay, A4 is on the slotted bar and it is very near to O2. Distance between O2 and A4. Distance between O2 and A4. Here we have 2 points A2 and A4. Okay, so distance between O2 and A4 is C minus R. That is C minus R times of omega of slotted bar into, that could be second velocity. Okay, both these velocities of slotted bar are not at all same, guys. Both are not at all same. Now, if we take the ratio, let us say this is equation A and let us say this is equation B. If we take the ratio of these two, we get this as omega of slotted bar of 1 divided by omega of slotted bar of 2. So we get this as C minus R by C plus R. Okay. So anyways, R into omega of crank and R into omega of crank, that is going to get cancelled. We will be left out with product of C plus R into omega of slotted bar of 1 is equal to C minus R, that is omega of slotted bar of 2. So now if you notice from the here, first the numerator is describing the distance difference of C minus R and the denominator is describing it's the addition. So definitely this value will be less than 1. And we know that omega slotted bar 1 is actually representing the cutting velocity. This is omega cutting. Okay. And this bottom velocity is representing omega return. Why? Because we are calling this mechanism as a quick return mechanism. So it is obvious the return velocity will be greater than the cutting velocity. We want the mechanism to complete the return motion quickly. So that is why we are also assigning, or we are writing quick return ratio as theta cutting by theta return. So you have to check sometimes. Quick return ratio, this could be either greater than 1 or this could be less than 1. So if it is greater than 1, we want the more time taken for the cutting stroke, and the time taken for the return stroke has to be definitely less. So when the time taken for return stroke is definitely less, the velocity of return stroke has to be more. Okay, so when quick return ratio, if it is less than 1, then you should be writing, or you should be expressing this as theta return by theta cutting. If it is greater than 1, then this is the formula we are supposed to follow. If it is less than 1, you have to just reciprocal it. Okay, so here we are able to realize same thing is happening in the return stroke, that velocity is maximum. So let us compute here the ratio of velocities. C is given as 250 and R is 100. So what will be the answer here? So this will be, the ratio will be, that is omega cutting by omega return, which is equal to 250 minus 100 divided by 250 plus 100 it is. So that is 150 divided by 350 it is. Okay. So 150 by 350 means approximately this will be equal to 0.56 or 57 or 0.6 approximately. This is 53s and this is 57s. So 7 fours are 28. 7 fours are 28 means this is 0.42 or 0.45 or 0.46 something approximately. We get the ratio as 0.41 approximately. We may get the answer. So this is the ratio of return velocities. Okay. So these are few problems, guys, few observations wherein I have taken an individual mechanism, and on that individual mechanism we were trying to estimate how differently the parameters can be asked in the various examination. Okay. So all the best for your preparation, guys.